Okay, let's talk about the exam. Hopefully, we're early enough in the semester that all the complaints about me not posting the exam you will forget before we do student evaluations. Okay. No, Carter is not going to forget.
May I request that you post a second exam early?
Yes, you can request that, and hopefully I remember. I should go set it up like now. Okay. Yes. Okay. The exam. Okay, so the exam, there's basically 10 questions. There's more than 10 questions because on some of them, it's like, this is a numeric problem, submit your work, and the submit your work goes on a different problem, right? So there's really 10 workout problems, but there's more than 10 problems because some says, hey, submit your work on the next problem because of how Learning Suite sets things up, okay? The problems are all going to be numeric problems, okay, which tend to be hard to get everything to work out. And here are, let me list out, I always make a list of everything that we've covered when I go to make exams. And so here's all the stuff that we've covered in no particular order. It's not chronological, it's not importance, it's just random order. Okay. So MOSFET switching. Okay, we talked about specifications like maximums on data sheets. We talked about level shifters, totem pole gate drivers, low side gate drivers, high side gate drivers. We talked about MOSFET characteristics like the RDS on. Yeah. Nope. Yes, it is found on my random piece of paper. That's it. So I can type it up and post it if that's what you want. Okay, I will do that sometime. Okay. And if you don't see it in a couple days, email me and then I can be reminded. So, but be nice and don't say you're a horrible person. Can you post it? So, okay. Okay, so all the stuff on MOSFET switching. And then we did a whole bunch of stuff on DC-DC converter circuits, okay? And the main thing with DC-DC converter circuits, since we're not doing LT-SPICE, we're doing analysis, it was all on that derivation. So being able to do a derivation of average voltage, peak-to-peak voltage, those kind of output voltages for any circuit that I give you. We did it for the buck converter, but you should be able to do that for any DC-DC converter circuit that I find, okay? And that's going through, and just to practice, the derivation was inductor voltage, solve for the inductor voltage and set the integral equal to 0, solve for the capacitor current, integral, set it equal to 0, and then you use the inductor voltage equals LdI dt and the capacitor current equals CdV dt. That's the derivation process for those. You should be able to do that. And then we did a whole bunch of stuff on DC motors, okay? The DC motors are more analysis than they are simulation, right? So we didn't really do LT-SPICE and all that kind of stuff for motors. So analysis exams is the perfect way to see what you understand on DC motors. So here are some lists of things that you can do for analysis problems on DC motors. Calculating speeds and torques, okay, from a DC motor, going from a DC motor circuit, finding the steady state speed. So if you have a specific motor and a specific load, you should be able to calculate a speed, and vice versa. If you're given that you want a specific torque and a specific speed, you should be able to adjust the voltage to get that. So either given the voltage, find the speed, or given the speed, find the voltage. So you should be able to go both ways, okay? You should be able to calculate torque, power, and efficiency for any type of motor problem. Moment of inertia, you should be able to calculate moments of inertia. And then we have acceleration, force, and torque. Now, this is not there is going to be Simulink, so it's not going to be plot out what everything looks like, but you should be able to calculate what is the starting acceleration or what is the acceleration at this point given these conditions. Okay, so you should be able to go from moment of inertia to acceleration. Okay, but not Simulink and all that. The exam is open book, open notes, open internet. You just can't ask humans. And if you can get the AI to, AI makes everything messy. So I don't know what my policy is on AI. So most of the time, I think if you can actually get AI to solve the problem for you, I don't know, but you should know how to solve these problems. So I'm going to say don't use AI, actually use your brain because I don't know. Yeah.
AI is really bad at this stuff,
Yeah.
so. But I think that that's kind of a non-factor.
That's what I thought, but I didn't know. I mean, AI is getting better and better. And it's getting to the point where it's encouraging people to stop thinking. And that has some implications, but it's going to be wrong on this stuff half of the time. Right. For some students, if they get half right, they're going to be good enough. I mean, if you're a top student, you're not going to use AI. If you're a bottom student, it might do better than you. I don't know. So I hope none of you are in that point because I think you're all have so much potential to not give up and use AI. So, okay. Okay. And then that's my whole list. Okay. Yeah. No, you're not good. This is all analysis. So everything has to be solve this problem, work it out. Now, you can use MATLAB or Desmos or Wolfram Alpha or any type of nonlinear solve thing you want to use is fine. Okay? Yeah.
When you said that there's like places for us to upload our work, are you expecting us to like handwrite, take picture and upload then to Learning Suite our work, or what did you mean by that?
Yes. In particular, DC-DC converter derivations, right? Because that's an actual derivation. The other ones are just work out some problems and get some numbers and all of that. But if you're trying to say, hey, you know, you got to do this derivation on solving for these things in DC-DC converter circuits, that's the part where there's a high probability that you'll need to submit your work, if that's what you want to know. So the other thing that we are going to do on the exam, when you have numeric problems, the average on exams tend to be low because you make some little mistake and all of a sudden you go from full score to 0. Okay. And that's really rough. Okay. So as soon as we're done with the exam, we're going to open it up with infinite tries to get half back on every problem. So we're going to do that so that you can fix everything. So the goal is for every problem, you'll get at least half on because you'll be able to do it over and over until you get it right after we're done with the exam. So we will do a regrade on it because the numerics tend to be really brutal, right? You miss one little concept and you go from full credit on a problem to 0, and there's nothing in between. So we will do a regrade on that to help buffer that pain a little bit. Yeah.
What did you say the time limit was on the?
Oh, so the time limit is a 3-hour time limit. I had one of the TAs take the exam and he went through it in detail, nice and slow, not taking too long, and it took him an hour and a half. Okay. Now, he's been teaching all of you along the way, so chances are the TA knows it a little better than you, and that's why you get double what it took the TA to do. It's hard for me because I know what the key to every problem is. It's hard for me to judge time because I know what the idea is when I made the problem. The TA doesn't. So an hour and a half for him, you get 3 hours. So it should feel rushed, but doable. Yeah. It was not Ammon. That's not fair. Right? Because he's a little too fast. Is that what you were going to say? Okay. No, it was Eric. What?
That was fair, is what I said.
Okay. Yeah. I mean, Ammons just runs things really fast, you know, you're saying that he's not a good indication of what's doable. Is that what you were?
Yeah, he's what I wanna be. He's my goal. I don't wanna be held to that line right now. Like, I wanna work towards it.
Okay. Okay. Any other questions on the exam? Okay, going after, so, the. So here's 13. 13 is design a converter that converts from 12 volts down to 5 volts. Okay, so we're doing a buck converter. Okay, but this one says that you're using an op amp to create the PWM signal. Okay, so let's go and look what that looks like. So here is our buck converter over here on the right, and here is our gate driver. So you see we put this is a PMOS on the top with the diode approach that we have. This is called an asynchronous, okay? And then typically we put in a signal that was a PWM signal, so a certain amount of duty cycle on. Typically in most of these, you don't create that, you put in some analog circuit that creates the PWM signal for you, okay? And that is done with an op amp, okay? So if I have an op amp without negative feedback, what happens? It goes rail to rail, okay? And so what we do here now is if we run this, almost there. So what we do now is I just basically have a voltage that I'm trying to get out, and I'm giving it a sawtooth signal, okay? So on one input of the op amp, I give it a sawtooth. On the other input, I give it a voltage, okay? And then whenever it's below, it's going to go to one rail. Whenever it's above, it's going to go to a different rail. And so the output here is a PWM signal. So typically how they create PWM signals is they take a sawtooth signal that they create, whatever signal that they want to do, and then you put a reference voltage and it's going to adjust your duty cycle based on where that is, okay? Yeah. Yeah, so typically they'll have sawtooth generators and you'll kind of do it. You can do it used to be in the old days, everybody did everything with analog circuits. These days, analog is slowly getting replaced by digital stuff over and over. You can make oscillators with unstable circuits so that you can make a natural square wave out of a transistor circuit or out of an op amp, right? You can make an op amp just oscillate. And you can convert a square wave into a triangle wave using an op amp integrator. So they usually create a oscillator and then they run it through an op amp to do that. So you can do it with analog circuits. For this class, we just say you have a sawtooth.
Got it. So to make a sawtooth, you would create an oscillator that just
Uh-huh.
and pulse modulate it, integrate it, and then send it into another op amp. And it would just a DC bias voltage that determines the pulse.
Exactly. Yep, that's what's done. And slowly as time go on, we start to replace some of these analog components with digital stuff because it's pretty easy these days to create just a PWM signal out. The issue is frequency. Because a lot of these DC-DC converters, we're trying to create custom PWM signals at 100 kilohertz, megahertz type things. And at some point it starts to get tricky for even the digital stuff. As the digital stuff gets faster and faster, it gets easier and easier to do. So, yeah.
Why would you do this instead of what we've been doing? Because at this point, you still need a digitally generated sawtooth and a bias and a power supply for your op amp. So
Yeah.
how's
So
that-
the reason why is that the sawtooth, we assume we have a sawtooth, okay? Now, at some point, this doesn't have to be a voltage. I can actually replace this with an audio signal. So if I replace that with an audio signal, it's creating the required PWM signal of a variable voltage going in. So now I can make that an audio signal, a sine wave, whatever I want, and it's going to create the PWM signal that I need to reproduce that average. And that's what's called a Class D amplifier, where I'm basically sending it in an audio signal and I'm trying to amplify it high efficiency. So what it does is it takes the audio signal, which is a varying voltage. We just show this at one point, but if that voltage goes up and down, the PWM period is going to change in time. Okay, so what you would do is you would put in your audio signal and compare it against the sawtooth. It would create a PWM signal. I would amplify that PWM signal and then filter it using this buck converter, and I get an amplified audio signal out. Okay, that's high efficiency and can handle watts or whatever you need to do. So did that make sense why you do that? Because it isn't just going to be a fixed voltage. Okay. Now, if you go buy in the shop or wherever you go buy a buck converter, they have a potentiometer on there where you can adjust the voltage that it puts out. That's because it's doing exactly this, right? It's reading it into a comparator, and you're adjusting the duty cycle with that potentiometer. Again, doing exactly like we're showing here. Okay. Now is that done with an op amp or done with something else? That's what you got to play around with. Okay. So that was this class activity. You know, you can kind of see what it is. We're going to come back to this comparator stuff later when we do inverters. And so I just wanted to jump ahead to 14. So here was 13 done really fast. Okay. Okay, so now we want to look at class activity 14, which is also a buck converter. And this time we want to do, we're going using 100 volts with a control that's a 3.3. So we're using a 3.3 volt controller to take a 100 volt DC signal. And we wanted to put out 25 volts with a high frequency with a power of 1 kilowatt. So we're taking, so now we've done these little 1, 2 watt, and we're doing a large scale PWM signal, buck converter. So buck converter with bigger voltages, bigger powers, and all of that. Okay. And now we're going to do this in LT Spice. So now we're going to combine our analysis that we did on buck converters with implementing our different configurations. Okay. This one will probably just go ahead and, you know, do we got to figure out, do I want to do a low side or high side, or how do I want to do all of this? Okay. So now we got to figure out how we want to do it. We're going to build this in LT Spice at these larger powers. Okay. So we're going to have to make sure that we choose components that can handle the powers that would work. Okay. The first thing that we want to do is, just because we're practicing for the exam, it would be nice to go back and rederive this and make sure that we can still derive all the equations rather than looking it up before. Let's kind of go through that analysis again really quick for this buck converter. In and P out was 1 kilowatt. Okay, so the first thing that we want to do is we want to kind of draw what our circuit is going to kind of look like. Okay, we're going from a high voltage to a low voltage, so we're going to be doing a buck converter. The simplest buck converter configuration is the asynchronous, where we're going to put a PMOS or an NMOS on the top, and then a diode. So the simplest case is going to be a PMOS on the top and a diode. Okay, so we're going to have a circuit. Gonna look something like this. Now, chances are how we do this stuff is gonna be a little bit more complicated when we go to LT Spice. We're gonna show the simplest version here first. Yeah.
Converter that you're making, they only output the specified voltage when the load resistance stays the same. Is that correct?
Well, the load resistance, given that if it was ideal, the output load doesn't depend on the resistance. Okay, in the project, it did a little bit because we're using real components. So once you use real components, the amount of power that you pull is going to adjust things. The load is always going to affect your ripple, but it shouldn't affect your average. Does that make sense? But it will always affect your ripple.
Okay, yes, that
Okay. Yep. And that's why we have to give a power when we give our ripple spec. Okay, so we have this. What is our process for deriving our equation? So what are we controlling in here? We have to calculate what is our resistance value, what is our inductance value, and what is our duty cycle. Okay, those are the things that we're solving for. Okay, inductance, resistance, duty cycle. Okay, how do I solve this problem? Yeah.
I like to start with the duty cycle because that's easy.
Okay,
E equals V out over V in.
and where did you get that?
We learned that in class a little while ago as
Okay.
the first design equation.
Yes, and how do we derive? And you're correct.
Yeah.
But just for practice, how do you derive that?
You can kind of think like, if we want out to be, say, 25 volts.
Okay.
Like what fraction of that is 100 volts, and just like that's our duty cycle, like 25.
Right, so you're looking at the average, right? You're saying, if I have something that's up and down, I want to calculate what the average is. So I know that the average is going to be the duty cycle. So 100 times the duty cycle equals 25. So my duty cycle is equal to 25 over 100, which is 0.25. And I think that this one said that my frequency is 100 kilohertz. Okay, so if we have 100 kilohertz, then I'm going to have a T on, which is going to be 0.25 times 1 over 100 times 10 to the third. And then I'm going to have T off, which is going to be 0.75. Looks like that. Okay. Okay. Now what? How do we solve the problem? Yeah. Yeah. Yes, thank you. How? Obviously, that's what we wanted. If you wanted to start with, what's the resistance value? Do we know what the resistance, which one's easier, the inductor or the resistor? Why is the resistor easier? It's just power. We know what the voltage is and we know what the power is, so it's a simple power Ohm's law-ish type stuff. So that one's going to be easier. Let's start with the easy one, and then the find the inductor value is the hard part. Okay, so how do I get, what's my equation for the resistor? Okay, so we have 10 to the third, 1 kilowatt is equal to V squared, which is 25 squared over my resistance. So 25 squared divided by 1,000. Did you get that, Joel? You have a calculator out, so.
base, which is 625.
Does that seem low, realistic? What? Yeah, I mean, because the thing is the higher your powers get, the lower your load resistances become. So when you're dealing, most of the time when we go through like 240 and 340, we're always dealing in low power systems, and our resistances will be in the tens of ohms, kilo ohms, hundreds of ohms, all that stuff makes sense. Once you get into high power stuff, our resistors become fractions of an ohm. right? And if I have a megawatt system, my resistances are gonna be milliohms, right? So the bigger your powers are, the smaller your resistors become. Since we're moving into power, they almost seem too small at the beginning because like we've never done with resistors this small before, but that's what it comes out to. In higher power stuff, you get lower resistances. Okay. How do we find the inductance? Yeah.
So. The balance of the inductance, oh, I don't know the equations, which is what you're asking for, I'm sorry.
Yes.
The balance of the inductance is, we need an inductor that's big enough so that we won't go rail to rail every time.
Okay.
Switch. But the larger we make our inductors, the lower for the longer we take the ramp up.
Okay.
And so some of the time, having a smaller inductor and turning it to capacitor.
Okay. And what is our spec that's going to be controlled by the inductor? The peak-to-peak ripple. So we're going to be looking for a specific inductor because we have a specific ripple. So we're going to want one value of our inductor because we specified the ripple. Now, if you are designing the system, you're going to say, oh, I want my ripple to be in this range, and then I get a range of inductance.
So what I'm hearing is I did the project wrong. Because I had a much lower peak ripple, it would specify a.
Right, but there should be one inductor that worked on the project.
If you have a specific peak ripple, yeah.
Okay.
Which one is less? So I'm hearing I did the project wrong.
Well, didn't I say you want a peak-to-peak ripple? I didn't say less than, I said design for this peak-to-peak ripple.
But the peak ripple is something you want to minimize.
Right, but a good engineering design doesn't over-design. You want to use the smallest possible inductor, which means that you want to design to a specific ripple. So, yeah, and we are out of time, so we're gonna end class, yeah.
Why would you want a specific, not something as low as possible?
Because you want to use the smallest possible inductor that meets the marketing specs. Right? Because the bigger the inductor, the larger it is, the more expensive it is. And so you have to design to a specific ripple with this. So you want to have the largest possible ripple because that gives you the smallest possible inductor, which is the smallest cost. Most of the time it doesn't. Yeah.
Smaller component.
Now there's always these trade-offs that we have to play with. So, but most of the time when I plug in my phone, if it's all 10 milliseconds to get there, who cares? Right? If it's going to be moving up and down, I'm using my buck converter to flatten out my voltage, then the timing matters more. If I'm just plugging in a phone, who cares? 5 milliseconds, 1 second? I mean, I don't really care. So, yep.
No project.
What do you want?
What do you?
We could build a Tesla.